Hello. As mentioned, I'm Tyler McMullen. I am the CTO of this company, and you can find me on the internet at @tbmcmullen. Great. So this talk says it's about isolation and about containers. It's definitely not about containers. Let me just put that out there immediately. Not at all about containers. I'm not qualified to talk about those, honestly. This talk is only about isolation in the context of multi-tenancy, right? When you need very high speed, very low latency multi-tenancy systems, isolation suddenly becomes a really interesting issue. So what do I mean when I say isolation here? So there's a bunch of different ways that we refer to isolation, right? So one of those is resource isolation, process isolation, fault isolation, and software fault isolation. These are all a bunch of different ways. We have all sorts of different ways of achieving these various things, right? So processes and containers, virtual machines, these are all kind of like different approaches to the same problem that we're trying to solve. Different ones solve it to different extents and with different amounts of overhead. So from my perspective, and this is a very informal definition, isolation is really being able to run some code without it affecting other running code in unexpected ways. So part of that is resource isolation, but we'll talk about that more in a little bit. Who here has heard of the term FDIR? Oh, one person. Yes, this is the first time that I've given this talk that anyone has known. That is awesome. So FDIR stands for Fault Detection, Isolation, and Recovery. This is actually a concept from control engineering, right? And is usually referring to monitoring things like thermal signatures, vibrations, oscillations, and so on, right? So it doesn't apply directly, but rather in a sort of metaphorical way. I like it because it separates out the three stages here. There's the detection stage, isolation, and recovery. Detection implies being able to tell when a fault has occurred, which is less trivial than it might seem sometimes, right? Isolation in our world means being able to prove that when a fault does occur, its blast radius is limited. And recovery for us means being able to ensure that the execution can be restarted and the system continues kind of oblivious to the fact that anything has actually occurred, right? In a computer program, I would say most of this comes down to two things, right? So there's control flow and there's memory safety. When I say control flow, what I'm talking about is the analysis of the set of possible paths that an execution of a program can take. When I say data flow or memory safety here, what I mean is the analysis of locations that a program can write to or read from, right? If you can work out these two things, you have actually solved most of the isolation problems. As we'll see, you can actually reduce these to just one thing, which is memory safety. And there is actually some open research at the moment about reducing them to the other thing, just control flow. But just to make it clear here, what I'm talking about is if I have some code and I want to isolate it, I want to be able to say that yes, if I call this function, it will be able to write to the area that I have allowed it to and not to other areas. Likewise, it will be able to call functions that I tell it it's allowed to, but not others. Okay. So when you examine what guarantees, if any, you have for control flow integrity and memory safety, what you get out is called a fault domain. And a fault domain is the answer basically to the question, what is screwed up if this program explodes, right? So fault isolation is really about reducing the set of possible faults to something that is knowable and recoverable. For instance, if certain code should not be able to be executed, fault isolation is about being able to prove that it's either not possible or that if it is possible, when it occurs, we can catch it and prevent it before any harm is actually done. So the project inside Fastly that I was working on when I first started looking at this problem had some interesting requirements to it. And we'll see why this is so different than most. So in this particular case, what I wanted to be able to do is isolate the execution, the internal execution of any individual request as it comes into our system. And we have thousands of nodes around the world, each of which are doing tens of thousands of requests per second. And the lifetime of these is generally under a millisecond, but up to 5 to 10 milliseconds. So this is kind of a weird situation to be in. Processes and containers and virtual machines don't really work for this. But let's kind of walk through it, right? So processes, right? So, I mean, what is a process? Well, if you look in the background there, that's actually the like task struct from inside the kernel. So it would seem like a process is really complicated. But if you think about it, what it really comes down to is that a process kind of has two parts to it, right? There's the memory, and then there's the metadata that's associated with the process inside the kernel. The metadata is not actually directly accessible by an executing process. From a process's perspective, it really is just memory. Like if you are inside that process, all you know is the memory that you have available to you. Otherwise, like it can access its own memory, but it really can't access anything else directly. Anything else that a process wants to get access to, it actually has to ask for help with, right? It needs to talk to the kernel to be able to get that. So essentially what I'm saying is that the memory region, that the memory space there, is the fault domain of a process. The biggest component of process-based isolation is this idea of virtual memory, right? Like virtual memory uses the hardware MMU and the kernel's VMA system to essentially give each process its own address space. This is probably like really well-known stuff to everyone in the room, right? But essentially this allows us to pretend that each process has its own memory entirely, even though it's actually sharing. So another key part of this is something that's probably like seems entirely obvious, right? It's almost as if there's no other way to do it. Code and data in the process model live in the same space. Process-based isolation works because if the only thing a process has access to is its own memory, and that is also where the code is, then we don't really need to care about control flow, right? If we decide that the fault domain is that memory itself, we don't really have to care what happens inside that memory region, right? And so we can just ignore the control flow problem entirely, stick the code inside of the memory region, and just like walk away, right? This is like a really important decision that was made like decades and decades ago, right? Because it ties us strongly to the safety properties of virtual memory. And it's kind of my opinion that this is why the Spectre attacks were such an important and big and scary thing for so many of us, right? Because that virtual memory barrier is the only thing separating our processes from each other. Right. The other thing that processes have access to is an interface with the kernel, which we refer to as syscalls, of course. These are calls that affect the process itself or allow communication with other parts of the system, right? So it's via syscalls that we give processes the ability to interact with other things. So for instance, if I ask the kernel to mmap me a file, that then modifies my memory region to give me access to that file. And that's the only way that I then have access to that file, right? And then if another process does the same thing, okay, now we both have access to the file. And so an interesting thing about this is that this actually allows us to extend a process's fault domain. And once we start doing this sort of thing, like processes actually start overlapping in their fault domains. Okay, containers are similar. Right? So containers follow the same idea, but then apply further resource isolation in terms of like PIDs and namespaces and syscalls and so on, right? But the basic idea is actually the exact same, right? So let's talk about a different way to do this. Let's talk about the concept of in-process isolation. How would you, inside of one of these processes, inside this thing that only knows about memory, isolate individual pieces of code and their executions? So I guess one thing that we might want to consider is like, why is this even interesting, right? So if we consider like these two different models for this sort of thing, right? If we have the process model and I want to interact, I have a process that wants to interact with another process. The way that we do that is by sending a message to the kernel, and the kernel's like, okay, I got your message, great. And then the other process is like, hey, do you have a message? Great, let me just get that message back. Right? So this is a multi-step process for getting anything done if you need to interact with each other, right? And so if you have things running in the same process, of course, you can just be like, hi, I can just reach over and just do the things that I want to do in your area, right? And so, right. On the one hand, we have traditional isolation techniques like processes and containers and so on, which are all too heavyweight for this sort of thing, right? And on the other hand, we have lighter weight techniques that are much more dangerous sometimes, right? If you try to take multiple different kinds of code and put them in the same process, you have very little in the way of guarantees, right? So what are we to do? Well, what we did, or what I'm doing, what our team is doing right now is looking at WebAssembly for this. We've been working on a project involving WebAssembly. So why WebAssembly, right? WebAssembly, and this is like my kind of like statement about why WebAssembly is super interesting, right? Because it's really cool for like making things run fast in a browser. That's great and all, but like why is it actually really cool? To me, it's really cool because it is the first fast, multi-language, retargetable, safe, intermediate representation that we have actually more or less agreed upon as a community, right? This is an intermediate representation that is used by multiple languages now, that is a first-class backend of multiple languages now. It's the first time that's actually ever happened, to the best of my knowledge anyway. So to me, this is really exciting, right? So in case you've never actually seen a WebAssembly program before, this is a text representation of one of them. There's a few interesting things about this. One is that memory is separated out, right? So we have like specific declarations for how much memory we want and what data is specifically going to be in that memory and at what locations, right? We have the functions themselves, which are typed, which is different than normal assembly code. And likewise, we have like explicit imports of functions, right? If your function isn't defined in here, we need to import it, right? There's no actual way to call a function that you can't import. And that's interesting. That's useful for us. So one of the key differences between a WebAssembly instance and a typical process is this. If you recall, a process attempts to take care of both like some level of control flow and memory safety just via virtual memory, right? WebAssembly is different. The actual code for WebAssembly execution is kept entirely separate from the memory. And one of the goals is to constrain the fault domain so only the memory is affected, right? So the code can be reused. This is very different than a process, right? If a process faults in some way, we can't then assume that the code is still good to use. You would have to reload the code, right? So this is like an interesting thing that is different about these. So we decided to use WebAssembly. How are we doing that? How do we actually ensure safety as we're doing this? So great, Clang, Go, Rust, all these things have WebAssembly backends right now. But the real question is like, how do you go from the WebAssembly into native code while maintaining, again, those safety guarantees, right? So what we've been working on is a compiler that takes WebAssembly and turns it into native object code, as well as a runtime that knows how to run that code safely, right? So effectively, there's a protocol between that compiler's output and the runtime that loads the code and executes it. Okay, so that really all just kind of starts the DL open, right? So our compiler outputs a shared object, and then you DL open it. Great. So part of the protocol that comes along with this is the calling convention, right? The calling convention, most people here are probably aware of it. Like, there's like the normal like sysv calling convention and all that, but we make some minor modifications to that in order to be able to ensure safety. So the first one is that the RDI register, which is typically used as the first parameter in a function call, it sets what we refer to as a virtual memory or a virtual machine context, right? So what is a VM context? So a VM context, so first of all, whenever we execute one of these WebAssembly modules, like we have our module and we can like create multiple instances of it, right? And so then we execute one of these instances. So the VM context in this case is actually a pointer to this location. So just up above that pointer, we have metadata that's associated with this instance. So those are things like global variables and like various other like internal system metadata pieces, right? And below that, we have the linear memory associated with that. Right, I actually had slides for that, great. So what's interesting about that is that if I want to access the memory associated with an instance, all I actually have to do is that, right? So it's very easy for us to go like, okay, like you want to access memory at like an offset of 16 from the beginning of the memory on this instance, great. You just do that with an offset from that virtual memory context pointer. Great. So one of the most difficult parts of this to do in a performance-sensitive way is bounds checking, right? So bounds checking is obviously like a pretty key piece of the safety involved in like actually ensuring that one of these instances, one of these executions can't actually affect anyone else or anything else inside that process. The problem with bounds checking is that like if I've read a bunch of papers on like people attempting to implement bounds checking inside of like say GCC or Clang. And the problem, of course, is that it's insanely expensive. It's really, really, really expensive. Typically, you would see somewhere between like 2 and 10x slowdowns for many types of programs. So WebAssembly makes this somewhat better as part of the model for that it uses for its linear memory. So if we look at like typical virtual memory, if I wanted to apply bounds checking to this, there are some complications, right? So one of them is that virtual memory typically can have holes. So if I want to access a block of memory that looks like that, I can't actually even just bounds check the beginning and the end, right? This actually gets significantly more complicated because of these overlaps, right? If I attempt to access there, I actually need to check multiple locations as I go through, right? So linear memory makes this somewhat easier. Linear memory, if you're not aware, is basically just like, it's just a block of memory that grows upward, and there cannot be holes in it, essentially is what it comes down to, right? So if I want to access a particular area of that linear memory, all I actually need to do is bounds check the end, because I can be assured that there are no holes below that. All right, but we can actually do better than that. So one of the things that my team has been working on, one of the team's things that inside our compiler that we spend a lot of time on is working on bounds check elision. So I should have warned there is going to be assembly in this talk, FYI. So in a naive setup, this one little line of code might expand to something like this in WebAssembly, right? So in this case, basically we're just getting the local for my array. Of course, WebAssembly is a stack machine based thing. So we push the location of our array onto the stack. We push a 0 because we want to write a 0. And then we call store, right, with an offset of 136, which is 17 times 8. Great. So if we were to compile this, and our linear memory model, like the model that we are using internally, is just a block of memory, right? So there's nothing special about this block of memory. It's just, let's say we malloc some memory. What would the actual generated code look like for this? Well, it would look something like that, right? So this is less complicated than it looks. Essentially what this is doing is we bounds check initially the original, like just the my array pointer right there. Okay, so first we bounds check that, and if it fails to bounds check, we do a UD2. UD2 just throws a sig-ill, right? So we blow up if it happens. Then we bounds check the offset from that place, right? And then finally, if all of that is actually cool, if that all works, then we have the actual instruction that we wanted to execute, right? So it's a multi-step bounds check. And this is, again, with linear memory, is still better than it would be with like regular virtual memory, but it is still not ideal. So let's take our naive setup from before and let's introduce the concept of guard pages to it, right? So let's say that we add a 4 kilobyte guard page. If you're not familiar with what a guard page is, it's really just we essentially just tack on a region of memory to the end of it that is non-writable, non-readable. In fact, it's not even actually taking up memory. It's really just saying, hey, this address space is unusable, right? So we just put that there. Right, so what does that get us? Well, given that we know that the index of 17 is within that 4 kilobyte guard region, all we actually need to do is bounds check the base pointer. Great. So we don't actually need to check the offset at all, and so we just check the base pointer. And this actually becomes more interesting if we have multiple accesses based on that base pointer. So if our code was changed to look something like this, we don't actually, again, need to check that bounds, check the offsets at all. Instead, we check that base pointer once, and then we can have multiple writes. So we can actually amortize the cost of that. Great. Okay, so let's say we take that model, right? So in that step we had our linear memory followed by a guard page. So let's say we extend that. Let's say we take that 4 kilobyte guard region and we actually turn it into 4 gigabytes of guard region. Okay, so what does that get us, right? Well, first of all, remember that WebAssembly addresses are 32 bits. right? So that means that all we actually need is nothing. Right. So given that the addresses, the pointers that we're using inside of a WebAssembly execution are 32 bits, it means that they can't actually access anything beyond that 4 GB region. So there is actually no way it's possible for it to need to be bounds checked, which is pretty neat. So one of the interesting things about this, though, is we try to have like safety in depth as we work on these types of problems, right? And so one of the things that I always worry about is, okay, well, what if the way that we compiled this program is wrong? What if our compiler has an error of some kind in it? And so what if, in addition to those UD2s, so the sigils and the seg faults that we would get from writing into these guard pages, what if we get a seg fault elsewhere? How do we know that the seg fault that we actually got from our instance is safe? How do we know that we can recover from it safely? And so this brings up the concept of trap tables. So one of the things our compiler does as it's going through the compilation stages, find all of these places that it knows that something can throw that it can trap, essentially, that it can be out of bounds, let's say, or there's various other things that WebAssembly can do that would require traps. So in this case, let's say we have a load, right? And that load just becomes some machine code. It looks like that. In addition to outputting that machine code, what we actually do is we actually output a trap site as well. And that trap site just says, okay, at this particular location within this particular function, so like a specific instruction offset within that function, we know that if it signals, if it throws an error of some kind, that error actually means the heap out of bounds. And the noteworthy thing about this is that, so we essentially develop this table of traps for each function. And what that ends up meaning is that if we see a trap that is not in this table, we know that something has gone horribly awry and we need to crash the entire system and burn down the building or something, right? Okay, great. That's enough assembly for me. So how are we doing this, right? So much of the actual work of this project is done in a project called CraneLift. So CraneLift is a code generator. It was specifically meant for WebAssembly, but also general enough for many other things as well. And so this is started by some folks inside of Mozilla. This is actually supposed to be like the next gen ahead of time JIT for Firefox. I'm sorry, not ahead of time JIT. Jesus, it's the JIT inside of Firefox. And what we are using it for is the ahead of time part of our compiler, right? Yeah, you can kind of think of CraneLift as like a smaller, lower level version of LLVM written in Rust, which is much more pleasant to work on. So we've developed a decent amount of code inside of CraneLift and on top of it, which ends up implementing the isolation scheme that I've been talking about throughout this thing. So it's been us and Mozilla and some other independent folks working on it, and we're always looking for people to help as well. So please reach out. So to review, isolation. Incredibly important to the way we build programs and do computation today, especially when it comes to multi-tenancy. But even for the reliability of trusted systems, right? Isolation is just as critical locally as it is when we're talking about distributed systems, right? So WebAssembly is a pretty awesome new way of implementing isolation in a much more lightweight fashion than we have been able to in the past. That's the thing that makes WebAssembly really exciting to me. However, one of the main goals of this talk was less about the specific technology and more about kind of challenging the way that we think about isolation. I feel like a lot of times we think about fault isolation in terms of specific technologies, when really what it is a set of concepts, and there are many different ways of approaching these things. So hopefully that has helped, and thank you for your time.
Let's give a round of applause. We have time for a couple questions if you get up and walk over to that mic right in the middle of the room. Don't be shy.
I think they're shy.
I think so.
Oh, geez.
So forgive me for sounding a bit ignorant here, but what actually is the application that this is being used for?
So the initial application so one of the things that Fastly has always allowed is for people to upload code that runs at our edges in response to requests that flow into the system, right? And we implement that in a way using a language that has like certain semantic limitations to it, right? And so the way that we do isolation at the moment is really just by saying like, okay, we're going to design this language in such a way that we know that it can't actually affect anyone else, right? And so this project was essentially my attempt at going like, okay, we have our safety and security requirement at this layer. Let's move it down a layer and see what that opens up for us.
Could you use the mic, please? I can give you one.
Sorry. So how would you go about retrofitting this to like legacy code?
How do you go about retrofitting this to legacy code? That is probably one of the hardest problems with this, which I didn't talk about in here, because it's also one of the more boring problems with it, right? It's more of a question of like how your software is designed to start with. So the way that this works at the moment anyway, is that it's actually like when you load one of these, when you have those imported functions, right, inside the WebAssembly module, those actually become undefined symbols in the shared object that we output, right? So it's actually just using the linker in like a very typical sort of way. But like the real trick with it is, okay, so if I want to pass pointers back and forth, right? For instance, one of them is 32-bit and the other is generally 64-bit, right? So this gets complicated quickly. So what we have designed internally is an IDL of sorts. So we actually design a way for us to say like, okay, if I want to import a function from the process that is running this isolation, this execution of WebAssembly module, here is like, I have essentially like an IDL of sorts that will let me output code that works on both the like outside of the WebAssembly module and also the inside of the WebAssembly module, and like translates back and forth for it. But this all does require that you still have like a very well-defined API in between there, right? Which if you don't, it makes it a hell of a lot more complicated. Yeah. It definitely would be a pain in the butt type of endeavor, yes.
So, thank you. I guess I've been listening to people talk about containers, and we use some VMs. We know that containers don't contain, and from a security perspective, they're not ideal. Listening to this and all the memory protections, assuming you wanted to maybe compile untrustable code down into a WebAssembly containment like this, and you wrote an API to accept inputs and calls from that logic, would you feel that would be like a very safe and high performance way for multi-tenancy?
So if all you had done is what I just talked about in this talk, then no is the answer. That would not be sufficient, right? So there's a lot more that would need to go into it, especially in the face of like the Spectre attacks lately, right? There's a lot of work that needs to go into that. Yeah, I'm not really sure I'm like prepared to answer that one ultimately, right? Like I think that it can be done with this, but it requires more work than just memory safety and trap tables essentially. But it can be done.
Would you guys be a company that would work that problem, or?
Yeah, that's a thing that we're working on.
All right.
Yeah.
Thank you.
Let's give a round of applause for our speaker.